10 minutes.
Good morning, professors and judges. I'm Ching from Ching Middle School, and today I'm glad to have the chance to talk to you about my project on non-torsion solutions of homogeneous linear systems over rings. And let's first consider a homogeneous system of M equations over a field K. Then there's always the trivial solution, and it's natural to wonder how many variables do we need to guarantee non-trivial solutions, no matter the choice of coefficients. And I'm sure every one of you would know the answer is n plus 1. So instead of considering a field, we now consider a homogeneous linear system over a commutative ring. Then we can ask the same question, and the key difference here is that not every element has a multiplicative inverse, so the row operations that we can perform are different. But after some literature review, the answer turns out to still be n plus 1. So instead of generalizing to other algebraic structures, we try to generalize the idea of non-trivial solutions, which will be non-torsion solutions in our paper. This is motivated from the following problem of the China Mathematical Olympiad 2021. Here, condition 2 is a system of two equations modulo k, which is just a system over the ring set or kz. And condition 1 is a stronger condition on the solution than non-triviality. It states that one of the coordinates of the solution have to be co-prime with k. The question then asks to find the minimum number of variables n, such that any choice of coefficients guarantees such a solution. And the answer turns out to be 2 times omega k plus 1. So to generalize the problem, we focus on the first condition and we can rewrite it into this form. Then we can rephrase the problem for a general ring. We'll define a solution to be non-torsion if the rephrased condition is satisfied. For example, in set mod 15 set, a solution is non-torsion if there is a coordinate xi which is not a serial divisor. And indeed, this definition works for any ring. So a solution being non-torsion just means that one of the coordinates is not a serial divisor. And we'll now introduce an important notation which will appear frequently. We'll define a set of non-torsion numbers to be a set of integers n, such that any homogeneous system of m equations with n variables guarantee a non-torsion solution. For example, if R is a field, then the set of non-torsion numbers is just all integers greater than m. And from the CMO problem, the set of non-torsion numbers with respect to the ring set mod kz is given as shown here. And the main problem of our paper is then to find the set of non-torsion numbers for any ring R. So firstly, notice that the set of non-torsion numbers must be of this form. That is, it must contain all integers greater than or equal to a certain number and not. So to determine a set is just equivalent to determining n naught. However, the task is in general difficult, so we split the task into two parts, which is to determine a lower bound and an upper bound for n naught. For the lower bound, it corresponds to constructing a system such that it only has torsion solutions. And for the upper bound, it corresponds to showing that a system of a certain size must have non-torsion solution. We'll first look at the lower bound. Inspired by the solution of the same problem, we consider the following matrix where Di satisfies these two conditions. By proposition 3.3, this would imply that Mn, which is the number of variables, is not a non-torsion number. So we have now reduced the problem from finding a system to finding the elements Di satisfying these two conditions. So we now consider the minimal primary decomposition of 0 and Pi as the radical of Qi, which are prime ideals. Then the decomposition exists if R is Noetherian. Then we should choose Di from Qi such that condition 1 is satisfied, and we should choose Di out of the union of the other Pj's such that condition 2 is satisfied. So a natural guess is to choose Di's from these sets so that both conditions are satisfied. However, these sets might be empty in some cases. For example, over this ring, one of the sets is empty because Q1 is a subset of P3. And the key observation here is that these sets might be empty when embedded primes are present. That is, one of the Pi contains another Pi. Namely, in this example, since P3 contains P1, one of the sets is empty. This motivates the following definition. We define the set of the radicals of Qi's to be a set of associated primes of R, and an associated prime is said to be minimal if it doesn't contain another associated prime, similarly maximal, and embedded if it is not minimal. We also denote these two sets to be a set of minimal and maximal associated primes respectively. And using a more refined strategy to choose the Di, we have the following main theorem, which says that if R is a Noetherian ring, then m times the number of minimal associated prime is not a non-torsion number. And the main idea in the proof is to choose Di in these sets which avoided the problem arising from n-variable primes. One could check that they indeed satisfy the two conditions, but the key step here is whether we can actually choose such DIs. So suppose that one of the set is empty for some I, then applying prime avoidance lemma twice, Qk would be a subset of Pj for some k and j. And this would be a contradiction to the minimality of Pj. This concludes the first section of our paper. Before we move on to this next, we noticed that from the previous results, some rings already have an empty set of non-torsion numbers. For example, these two rings. So instead of finding elements in the set of non-torsion numbers, we will instead focus on considering when would the set of non-torsion numbers be non-empty. That is, we'll try to find sufficient and necessary condition for non-torsion numbers to exist. To do that, we'll first have two correspondences. The first one is, which is shown here. The first one is a standard correspondence, and the second one is a correspondence between module homomorphisms and surjective maps from M, which is a submodule of Rm, to the products of R mod Pi, where Pi are the maximal associated primes of R. And the key step in reducing the problem is the following definition. We define a new set called non-tor PRM to be a set of integers n such that one of the following equivalent conditions is satisfied. And notice that it comes from the previous second correspondence that these two conditions are indeed equivalent. And defining such a new set allows us to consider one prime at a time. And the main result in this part is the following theorem, which says that if we can find NP in non-tor PRM for each maximal associated prime P, then we can also find a number n in non-tor Rm. So this means that the problem is now reduced to finding elements in non-tor PRM. But how can we do so? Notice that this is equivalent to finding n such that there are no submodule M of Rm, where M can surject to R mod Pn by definition. And the following theorem is our first attempt in providing an element in non-tor PRM. It says that if any submodule of Rm is generated by k elements, then k plus 1 is an element of non-tor PRM. But when will submodules of Rm be generated by k elements? The following lemma answers this question, and it says that if all ideals in R can be generated by G elements, then submodules of Rm can be generated by Mg elements. And the proof is modified from one of the reference textbooks, which handle the case when G equals to 1. Combining with the previous theorem, we have the following corollary, which says that if all ideals in R can be generated by G elements, then Mg times the number of maximal associated primes plus 1 is a non-torsion number. But numbers of generators of ideals in the general ring is often unpredictable. But numbers of generators of ideals in a local ring have been well studied. Namely, we have the following theorem, which says that if R is a local ring, then the numbers of generators of ideals is bounded in R if and only if the Crow dimension of R is less than or equal to 1. So we wonder, can we reduce the problem to a local setting? So we consider the localization of R instead, which is a local ring with the maximal ideal PRP. And the key theorem is as follows. It means that non-tor PRM is preserved after taking localization. So we finally have a sufficient condition for the set of non-torsion numbers to be non-empty, which is the following main result. It says that if the height of all maximal associated primes is less than or equal to 1, then the set of non-torsion numbers is non-empty. And the proof is as follows. If the condition is satisfied, then all ideals in Rp can be generated by G elements for some G. By our lemma, this means that any submodules of Rpm can be generated by Mg elements. And so Mg plus 1 would be an element of non-tor Prm. And this would imply the result by theorem 4.8. In fact, after the submission of this paper, we realized that the main result is actually a necessary condition as well. So we have the following refined main result, which is an if and only if condition. This means that, surprisingly, the existence of non-torsion numbers is precisely governed by the height of the associated primes. And I've also included the proof here, but due to the time limit, I wouldn't have time to cover it here. So if you are interested, you can ask me in the Q&A section. To conclude, our paper is split into two parts. And in the first part, we have shown that if R is non-variant, then M times the number of minimal associated prime is not a non-torsion number. While in the second part, the main result is that if R is non-variant, then non-torsion numbers exist if and only if the height of all maximal associated primes is less than or equal to 1. And the main tools used is also shown here. This is the end of my presentation. Thank you.